Okay, let us start the class. People who are coming, I will keep them admitting, but please, I will request you to join the class around about 10:30. All right. So let us start the class and okay. So I was trying to explain convolution in the last lecture, and in the last lecture we saw that how the principles of homogeneity, the additivity, and linearity resulted in the convolution expression. But if you try to understand the basic process involved in the convolution, that what exactly is convolution, and you want to visualize what are the basic steps involved in the convolution. So there are 4 basic steps to the calculation. One is that if you have 2 sequences, one is hn and the other one is xn, the other one is hn, then the first step is the flip operation, right? In one of the sequences, you have to flip the sequence by h of minus k. Then you have to keep shifting the sequence by varying the values of n. First, it will be h of minus k, then 1 minus k, 2 minus k, 3 minus k, 4 minus k, or minus 1 minus k, minus 2 minus k, minus 3 minus k, and so on. And you have to calculate, you have to compute the expression for all values of n. And you will see that if it is a 4 point sequence, right, in both the cases, then you will see that after about 7 points, the resultant sequence will become 0. Most of the values after that will become 0. But you are supposed to compute all the values. That means all values for n going from minus infinity to even infinity. Then the third operation is the multiply operation, where you will multiply the shifted and the flipped sequence hn with xk, right? And the last operation is the sum operation, where you will sum it for all values of n, right? Let us see how this can be explained. Okay, let us see how this can be explained further. Okay. Now, this is one of the examples that I will take to explain the graphical method of convolution. Let's say 2 sequences are there, hk and xk. All right. So these are the values like this. For so this point, you can say is the origin point. First of all, you will have to, I would request you to see, okay, let us see this h of minus k first. This is hk sequence. So these values are -1 here, 2 and 1 here. And if you will see h of minus k, so 2 remains there, right? So 2 remains as it is. These -1 and -1 will come to the left of the 2, and this 1 which is earlier on the left will come to the right, because you are doing the flip operation h of minus k. And once you do the flip operation, then you will have to multiply the sequence h of minus k with xk. That means you will have to multiply the corresponding values. If you see this value is 1. This will be multiplied with 2, right? And this value is 1. and sorry, this value is -1 will be multiplied with 0, so it will be 0. This -1 will be multiplied with 1, which will be -1. This 2 will be oh, I'm actually, I have to multiply h of minus k with xk. So let's once again do it. This -1 is there after the flipped operation is done, right? -1 will be multiplied with 0, so it is 0. This -1 will also be multiplied with this 0, again it is 0. This 1 will be multiplied with this 2, and this 0 will be multiplied with this one, which is actually this calculation y of 0. If we are calculating y of 0, that means for n equal to 0, 1 will be multiplied with 0 and 2 will be multiplied with 1. The output will be 2 for y0. The point is that you have to multiply the corresponding values. Then you shift the value and move you move the hk sequence to left, right, by h of -1 minus k. That means n is equal to -1 here. That means you are calculating for y of -1. And if you multiply the corresponding values in xk, you will see that if you will multiply the corresponding values of this sequence and xk sequence, you will see that the y of -1 will be equal to 1. Similarly, you even shift the hk sequence one step towards left by putting n equal to -2, and you calculate the value again by the same method. You will see that y of -2 is 0, y of -3 it will also be 0. Now you will have to calculate the values on the right side of the sequence, right? Okay, now you have to shift the hk sequence towards right by putting n equal to 1. So that means this was your hk. Now this point will come, if you see here, because what is the flipped version? The flipped version will actually shift towards towards right. But if you have to implement h of 1 minus k, first operation will be you will have to fold the sequence hk, then you will have to shift it towards right for implementing h of 1 minus k, and you multiply the corresponding values. You will see that h of y of 1 comes out to be -2. And if you do for h of 2 minus k, still you shift hk sequence, the flipped version of the hk sequence towards right once 1 unit of time. So y2 you will get as -2, y3 you will get as 1, y4 you will get as 1. All the rest of the values for y, for various values of n corresponding to the output will be zeros. All right, this is the graphic explanation of convolution. The moot point is that there are 4 basic operations involved in the convolution process. The first operation is the flipping of one of the you have to take one of the sequence and you have to flip that sequence. You have to keep shifting the sequence for various values of n. You have to multiply xk, xk is the other sequence, with the hk sequence. You have to sum. That's the basic. These are basic 4 steps involved in the calculation of the convolution or linear convolution of 2 discrete sequences. All right. I hope the things are clear. I know that you have already done it, but you will have to write a program for this in the lab using MATLAB. Okay. Now, what actually is convolution from the intuitive point of view? Therefore, convolution is a way to combine 2 time series, right? 2 time series means, as I have taken in the example, 2 discrete sequences I take. So those can be said as the 2 time series, right? Now, this is a way to combine 2 time series. Either the time series can be one time series or it can be images. your 2D time series, right? To create a third time series, because the in the previous example we saw that there is a combination of two time series, right? Two discrete sequences. The output is also a discrete sequence. Now, what is the what are the two time series? One can be signal, right? The interesting time series, it can be data signal or any kind of signal. The other we call as the kernel, the filter. Normally, what we see here, xk's are the inputs, and hk's are the impulse response of the filters. All right, impulse response of but we will come to that point maybe afterwards when we will go to the filters part. So this is all about the convolution, about the linear convolution. Now let us see at the stability of linear time invariant systems. A linear system is stable. We have to check for the stability of the system. Now, a system is stable if and only if the stability factor denoted by S, and it is defined by the stability factor. It is if the mod of a sequence is less than infinity, where k going from infinity to infinity, meaning by if the summation of the mod values of the sequence are less than infinity, then we will say that the system is stable. Let's see further how can we. Now let xn be a bounded input. The question is that we have to go for BIBO, meaning by bounded input and bounded output. Let xn be a bounded input sequence. Mod of xn is less than m for all m. So that's the point where m is some finite number. Modulus of xn, which is the input sequence, is less than m. That means we have bounded the input sequence. Now we must show that the output is also bounded. If the input is bounded, we must show that the output is also bounded. Then only we can say that the system is a stable system. Let's take one or two examples. I will come to the example straight away. Okay, let us check the stability of the first order recursive system. So this is the system. If this is the difference equation of a system where yn is equal to a yn minus 1 plus xn. This is the recursive system because there is a feedback path. There is a path showing that the output is being fed to the input. Now, what the impulse response of the system? If you take this system, the impulse response, and if you calculate the impulse response, as I was trying to explain you in the last lecture, you will see that the impulse response is a to the power n un. Now, we have to prove that we have to prove the stability of the system. We will check that as we will check with this. We will take the modulus of this, and we will apply the summation, and we will see whether the value comes out to be finite or not. So let's see. It is obvious that S is unbounded for modulus A greater than or equal to 1, since then each term in the series is greater than or equal to 1. If you see this value, modulus of, if you put the value of Hn here, so it will be a to the power n, modulus of a to the power n, where k going from minus infinity to infinity. You can even replace this k from 0 to infinity, because this un will be existing only from values more than 0. All right. Now, it is obvious that S is unbounded, because the values, for values of a greater than 1, this function will become unbounded, as since then each term in the series is greater than or equal to 1. But for mod A less than 1, if mod A is less than 1, then it will be geometric sum. It will be a GP series, and you will see that the summation of the series is S is equal to 1 over 1 minus modulus of A. for mod A less than 1. So that means here S is finite. So we can say that S is finite for mod A less than 1. The system is stable for mod A less than 1, but system is not stable for mod A greater than equal to 1 because the output is not bounded here. So for proving that a system is a stable system, we have to take an input which is bounded input, and we must be able to prove that the output is also bounded. Then only we can say that the system is stable. All right. Okay, these are some of the basic operations, basic signals, and basic systems, properties of the systems. These are which define, which are basically the review of the signals and systems course, right? But let us also keep reviewing and start with the introduction to Z transform. And we will go through the Z transform. After that, we will go through the DFT and all. Then we will almost finish with the review part, and then we will start with the digital filters. But let us try to understand the introduction to Z transform first, right? This is a kind of I have already explained that if a signal is there in the analog domain, which means continuous time domain xt. Let me explain this diagram. This is the crux of the signal processing situation put in one diagram only. So let us try to understand this. This is analog domain. Xt is the continuous time signal. We know that how to get the sampled version of the signal. That means the discrete time signal. You replace the t values with n capital T, where t is the sampling interval. Now, in the analog domain, what you do? In the analog domain, if xt is the signal, you apply Laplace transform. But in the discrete domain, if xn is the sequence, right? After you sample the signal and you make it a discrete time domain signal, you apply Z transform to get xz. In a continuous time domain or analog domain, you take the Laplace transform and you transform it to x of s, where the parameter is s in analog domain and the parameter is z in the discrete domain, right? Now s is equal to basically sigma plus j omega, capital omega. But if we have to take the frequency response, then we put this sigma value equal to 0. So once this value is put equal to 0, we can say that s is equal to j capital omega. So that means x of capital omega is the frequency response in the continuous time domain. What happens in the Z domain? We start from the sequence, we take the Z transform, we get xz. Now we replace every z with z equal to e to the power j small omega. We get x of e to the power j omega. This is the frequency response in the discrete domain, or the Fourier transform in the discrete domain. This is the Fourier transform in the analog domain, where small omega is the digital frequency. The relationship between the small omega and the capital omega is small omega is equal to capital omega into capital T. What is capital T? Sampling period. What is this capital omega? This is analog frequency. What is this small omega? This is digital frequency. Now, if you replace capital omega by 2 pi fa, so and you replace this capital T with 1 over fs, which is the sampling frequency, you will get this formula. I have already explained this formula. And this fundamental period, please remember that this is very important. The fundamental period of this analog frequency exists from -infinity to infinity. But the fundamental period of the digital frequency is from -pi to pi, because beyond this, we saw in the sampling that the digital spectrum is actually same as the analog spectrum, but the digital spectrum will repeat. There is a repetition of the in the digital domain, in the discrete domain, repetition of the analog spectrum with a period of 2 pi. All right. So therefore, the fundamental period where the digital frequencies will exist is from minus pi to pi. Now, if we express it in the graphical form, what is the continuous domain? How we can represent the S plane? Because S is equal to this sigma plus j omega, j capital omega. So sigma, this sigma is on the x-axis, j omega is on the y-axis. And what is the stable region for, what is the stable, how can we prove the stability in the analog domain? If the pole locations are on the, we will come to pole and 0 point. So this is the stable, the left side of the j omega axis, that means the imaginary axis. The left side of the imaginary axis, j capital omega, is the stable region. Now what we actually do, we take this j capital omega axis, this axis we take, we make a circle, all right, and whatever we wrap around every portion in the on the left side of the region, right, and put and confine every portion into a circle. So this becomes the stability in the Z domain. So this is the Z plane. In along the x-axis, so Z is a complex variable, right? Along the x-axis is the real part of Z. Along the y-axis is the imaginary part of Z. How this value, this point is actually small omega equal to 0. As we move anti-clockwise, right? So the frequency is either pi by 4, pi by 2, 3 pi by 4, pi, and so on, right? It comes to pi, then it goes from minus pi, like this it goes, and it comes back to 0. So this is digital frequency. This is how the rotation vector of the digital frequency will move. And what is the stability region? Inside, excuse me. Inside the circle will be the stability region. So that you can say is the relationship, that's the introduction and the relationship of the analog frequency and the digital frequency, and how you will handle the things in analog domain and how you will handle the things in the discrete domain, right? Okay. Now the primary role of Laplace transform in engineering is transient and stability analysis of a causal system, because this sigma, it will define the transient response of a system. This capital omega defines the frequency response of the system. So therefore, what is Laplace transform doing in engineering is transient and stability analysis of causal LTI system described by differential equation. If you remember, in my first lectures only, I said that analog or continuous time systems are represented by a differential equation. Now, what is the role of the Z transform? The primary role of Z transform are the study of system characteristics, derivation of computational structures for implementing discrete time systems on computers. The transform is also used to solve difference equations. So clearly, the difference is there in the Laplace transform and in the Z transform. So it must be clear, you know. Sorry. Okay, so what is that? Let's start the Z transform. So what is Z transform? The Z transform of a discrete time signal is given by Xn is the Z transform of Xn is the discrete time signal or discrete time sequence. It has to be multiplied with Z to the power minus n, and going from minus infinity to infinity. This is a two-sided transform, right? Where n, which involves n going negative values of n also and positive values of n also. So it's a two-sided transform. And what is Z? Z is in the polar form, it can be represented as R e to the power j omega, right? Where small omega is the digital frequency, where Z is a complex variable. Now in causal systems, Xn may be 0 when n is less than 0. We know that in causal systems, for n less than 0, the value of the signal is 0. So we can then define as Xn equal to n equal to 0 to infinity, Xn Z to the power minus n. So this is a one-sided Z transform. We will talk about one-sided Z transform also, right? Okay, let me. Okay. Clearly, the Z transform is a power series. If you see, this is a power series Z to the power minus n. It is clearly a power series with an infinite number of terms, and so may not converge for all values of Z. So if this is a power series, this may not converge, may converge depending on the situation, right? So, okay. So it may or may not converge. The region, this is important, the region where the Z transform converges is known as the region of convergence. And in this region, the values of xz are finite. If the region which is not region of conversion, the value of the values of xz will be infinite in that case, right? The step sequence xn equal to, let's say if a sequence is there xn equal to 1 and n goes from 0 to infinity, n goes from 0 to infinity, and it is 0 for n less than 0. Now if you take the Z transform, applying this formula, xn is 1 for values of n going from 0 to infinity. If you apply this formula, you will see that you will get xz is equal to 1 plus z to the power minus 1, z to the power minus 2, and so on. So this is a geometric series with a common ratio of z to the power minus 1, right? The series converges if z to the power minus 1 is less than 1, or equivalently mod z greater than 1. So we can say that this is a GP series, infinite GP series. So what is the sum? 1 over common ratio is z to the power minus 1, 1 over 1 minus z to the power minus 1. So you can get this z over z minus 1. All right. For for mod z greater